bar, for the purposes of my lectures of this chapter, where I am going to use the Bose distribution function and Bose distribution, Bose-Einstein distribution only, I will omit index b. So for whatever I write during next 5 lectures, it assumes that n bar, or sometimes I will even write it without bar, means that this is a Bose distribution function. So this is 1, p equal to 0. This is 1 divided by e to the power minus mu over temperature minus 1. But the average number of particles occupying state characterized by p equal to 0 should be not negative. So this is n is larger or equal to 0. Right? Because the average number of states cannot be negative. It can either be positive or 0, which means that e to the power minus mu over temperature is larger than 1. Or, well, larger than 1. Which means that chemical potential is negative. Let me say more accurately, not positive. So, this is very important property. What does it mean? How to approach the chemical potential equal to 0, and if there is a way to approach it. Let's now write n bar p equal to 0, assuming that chemical potential is approaching to 0. We assume that there exists some temperature T node at which chemical potential, I remind you that the chemical potential is function of the temperature and density of particles. So this is a potential. So if chemical potential approaches to 0, we expand exponent 1 plus modulus mu over temperature minus 1 plus and so on and so forth divided by 1. So it's equal to temperature divided by mu. So if chemical potential goes to 0, then the average number of particles goes to infinity. If we write it schematically, so this is the chemical potential, this is function of temperature. So at certain temperature T node, the chemical potential becomes 0, and it remains 0 for all temperatures below T node. This phenomena, when the average number of particles occupying quantum state characterized by 0 momentum, and if this average number becomes macroscopically large, we are dealing with something like 10 to the power 23 atoms, known as Bose-Einstein condensation. Bose-Einstein condensation. So there is a macroscopic number of particles occupying state characterized by 0 momentum. Namely, we are not talking about condensation in real space. You know, if you have an image that you have a vapor, you have a metallic plate, and the water condenses on the plate, this is a wrong image. This is condensation in real space. Now we have a condensation which assumes, as I said, that macroscopic number of particles is occupying state characterized by 0 momentum. How to find this temperature equal to 0? As I said, the total number of particles in the system, this is sum over P. Again, you remember that I'm talking about state characterized by 0 spin. There is a no degeneracy factor, and here n p bar. As usual, I will place it as integral volume integral dp over 2 pi here we have a Bose distribution function e to the power epsilon e
excuse me,
plus
Professor.
modulus mu, because chemical potential is negative, divided by temperature minus 1. This equation is defining chemical potential as a function of temperature and density of particles. If you resolve this equation as a function of temperature and number of particles, you get a function which is chemical potential. This is a way how to plot this curve. However, we said...
Excuse me, sir, there's a question. There's a question. Jonah.
Hello, yes, sir, can you hear me?
Yes, yes.
Yes, so you talked about Bose-Einstein condensation, and what we just calculated is that the occupation number for zero momentum goes towards infinity. There is so much occupation at that point, and then you also mentioned that this indicates that this is not a condensation in real space. So my question is that this condensation is in what space? That is one. And secondly, is this, this goes to infinity, then this is a macroscopic occupation, I think.
I'm coming to that. So to answer your question, this is a condensation in the momentum space. So macroscopic number of particles occupied state with a momentum or energy equal to 0.
Yes.
So, but then, this is what I'm going to tell you next. I'm going to define this T node, first of all, and then we will see how to actually treat this sum correctly and what this infinity means. Okay. Because we have a system with n particles, but n is terribly large. It's 10 to the power 23, 10 to the power 24, and so on and so forth. This is what infinity means. So, first of all, the plan for next 5 minutes. First of all, to find T node and connect it with the density of your particles, the same way as we connected Fermi energy with the density of fermions. And second, we will relook to this sum, and we will define it in a proper way. Because there is a paradox in what I'm writing. This paradox does not exist for temperatures larger or equal than T node, but paradox appears if temperature is smaller than T node. But let's first find this T node.
I see.
Okay?
Okay, I see. Yeah.
So, at temperature T equal to T node, we said that chemical potential is equal to 0. So then we will plug chemical potential equal to 0 and T node in this equation. So N over B in the left-hand side is equal to integral. I will treat in the very same way as I did for them. Fermions, namely, I come to the energy unit. So the spectrum is isotropic, it's p squared over 2m. Therefore, I will come to the spherical coordinate system. I will integrate over solid angle. It will give me 4 pi. Here I have 8 pi cube h bar cube. And then, since energy is this, so d energy P is equal to P over m dP. Therefore, I will write m. I will write square root over 2m, and I have integral from 0 to infinity, square root of energy, d energy, times 1 over Bose distribution function, e to the power energy over T node minus 1. Okay? So, the next step, I need to make my integral dimensionless. Therefore, I will divide by T node, and here divide by T node to the power 1/2. This is epsilon over T node is going to be dimensional variable, and then I'm going to multiply to T node to the power 3/2. So the rest, namely integral from 0 to infinity, dz. Square root of z divided by e to the power z minus 1 is a constant. It's expressed in terms of Bernoulli numbers, but I'm not going to calculate this integral. This is a constant, just a number. So therefore, we can express T node in terms of the density. And we get that T node is equal, if I take into account this constant, which is 3.31 h squared over m times density to the power 230. We have a density here, we have a T node to the power 3/2. So this is what we get. This is a temperature at which Bose-Einstein condensation starts. Okay? Now, let's look at this paradox. And let's first of all identify what is the paradox. If we treat this integral at temperatures below T node, in principle, we can do the same. We put instead of T node actual temperature, and we will get the density is proportional to the temperature to the power 3/2, and therefore, if temperature goes to 0, the density goes to 0, which is a nonsense, because density is given to us. We have a certain number of atoms in given volume, so the density is fixed. What is wrong? And what is wrong, that below temperature T node, we cannot treat the sum like we did before. Namely, we need to take into account that there is a macroscopic number of particles, so density n over v, or number of particles, better to say, is equal to, we write separately term with a p equal to 0, n node, plus sum over p, and p bar, not equal to 0. And we are saying that this number of particles occupying state with zero momentum is macroscopically large. Therefore, what we get by doing this integral, we get a number of particles occupying the states with non-zero momentum. And therefore, we can write down that the number of particles n node occupying being in Bose-Einstein condensate state is given by n, and here we have 1 minus T over T node to the power 3/2. Indeed, if temperature, so this is for temperatures, by the way, this expression is valid for temperatures smaller or equal to T node. Indeed, if temperature is equal to T node, we just have no particles being in Bose-Einstein condensate. But if temperature is approaching 0, we have almost all particles being in the Bose-Einstein condensate state. So indeed, T node is the temperature below which phase transition occurs. So we have a change of our ground state. And we discussed this example of phase transition when we have a lecture about classification of the phase transition. I will put it as a problem, but those who will be able to solve it now, you're welcome to do it. Those who are not able to solve it, please wait for basically wait for 2 weeks. The question which I'm asking is, what is the order of the phase transition? Some of you heard about first order phase transition, which is typically transition from the liquid to vapor or from the liquid to ice. Some of you heard about second order phase transition, which are the transition from ferromagnet to paramagnet or from normal state to superconducting state. What is the order of this phase transition? We discuss it in more details. So, summarizing, we coming from the symmetry grounds that the wave function is fully symmetric. With logics, we arrive to conclusion that the occupation number of given quantum state can be arbitrary. We derive the Bose-Einstein distribution function, and with the help of this Bose-Einstein distribution function for three-dimensional case, I emphasize that this is very important. I am discussing three-dimensional case because it's in two dimension the story is a bit different. In one dimension there is no Bose-Einstein condensation. So in three-dimensional case, we derived a temperature at which ideal Bose gas, no interaction whatsoever, undertake the transition into the state where the macroscopic number of particles occupy the state characterized by zero momentum or zero energy. And this phenomenon is known as a Bose-Einstein condensation. Any question about that?
Professor?
Yes?
Can you repeat the part where you divide the case t smaller than t0 and t greater than t0?
Yes. The logic is the calculations which I did here for t0 are completely valid because my assumption is that for t equal to t0, the chemical potential becomes zero. So these calculations are completely valid, and I identify and I connect this temperature T0 with the density of gas. By the way, this connection is pretty the same as we got for Fermi energy, which is for three-dimensional electron gas is also proportional to the density to the power 2/3. Then I'm saying that if we formally look at this expression for temperature smaller than T0, and we are saying that everywhere for temperature smaller than T0, chemical potential remains zero, that formally this calculation should be valid. And along the lines of what I did on the blackboard, I just replaced T0 by actual temperature T. And what I get in the wrong calculations, that N over B is proportional to T over T node to the power 3/2. And moreover, the density which stands in the left-hand side going to zero is going to zero if temperature which stands in the right-hand side goes to zero. And this is a nonsense because the density in the left-hand side is fixed. It cannot go to zero. And in order to resolve this paradox, I was saying that the paradox was connected that I erroneously treated this sum. I replaced this sum by integral for temperature smaller than T0. But I'm not allowed to do it because I have Bose-Einstein condensation phenomena. Namely, there is a macroscopic number of particles occupying zero momentum state. Therefore, in this sum, I should treat separately term with a p equal to 0 and term with a p not equal to 0. With the term not equal to 0, I proceed the very same way. So this is not n over v, this is n prime over v, where n prime is a number of particles staying out of Bose-Einstein condensation. So at any given temperature below T node, you have a mixture of particles occupying the state with a zero momentum, zero energy, and you have particles occupying state with a finite momentum. So what we calculated along the lines of the procedure explained on the blackboard is just a number of particles occupying states with a p not equal to 0. If I collect this and use that n node plus n prime is equal to n, I can express a node in terms of total number of particles or total density. If you want, I can divide left-hand side and right-hand side by the volume, and I will get the same equation for density, which depends on the ratio of a T and T node. So this tells me how many particles are in the Bose-Einstein condensed state at temperatures below the Bose-Einstein condensation temperature. In particular, it tells me that if I take temperature equal to 0, that all particles are sitting in a Bose-Einstein condensed state. The mistake, naive mistake, to treat this equation at temperatures below T node was incorrect treatment the sum. This is an incorrect treatment the sum. This is a correct treatment of the sum. Okay? Now, I in order to be able to tell you about Gross-Pitayevsky, actually I presume that this Bose-Einstein condensation you discussed in the course of statistical mechanics. Did you?
Yes, we did.
Yeah. So mathematics should be clear. I would rather concentrate on physics. So in the next 10 minutes, I will discuss thermodynamics of the Bose gas. I will derive the equation of states, which by the way is going to be the same as for fermions, but I will derive it to you using a bit different method to show you how people can vary the method. And after it, we come to discussion. For example, this equation of state connects the pressure and the energy. We discuss physics of Bose-Einstein condensation, namely the particles sitting in the condensate. This is a jargon or argon, are not contributing to pressure, and this is obvious. And then we come to Gross-Pitayevsky. The only comment which I would like to make it is related to the problem which we treated before. Namely, we considered bosons in a box. But more realistic and more experimentally relevant situation is that people confine bosons in a trap. Optical trap, putting optical pressure in order to combine particles, or magnetic trap. If atoms are characterized by internal moment, there is a combination of optical and magnetic trap. I will show you some slides on the 5th lecture about, or 4th lecture about Bose-Einstein condensation. So typically, we don't have free particles. We have a particle, say, in parabolic trap, which, as you know, characterized by equidistant levels. So what does it mean, Bose-Einstein condensation in the parabolic trap in particular? You can have any other trap. You can quadratic parabola, you can have some other potential which will not characterize the equidistant level structure. The Bose-Einstein condensation, which then for box relates the macroscopic number of particles occupying the zero momentum, which is the same as zero energy state, in a trap means that there will be macroscopic particles occupying the lowest level in your trap. In particular, for harmonic trap, you have a 0-point motion, so your spectrum is h bar omega node, the frequency characterizing the trap, n plus 1/2 if you have one-dimensional trap. It will be n plus 1 for two-dimensional trap, n plus 3/2 for three-dimensional trap. So you have a 0-point motion, namely your level is not at the bottom of parabola. So for the trap, your chemical potential will not be equal to 0. It will be equal to this energy of 0-point motion, and then you will have a macroscopic number of particles occupying the lowest possible energy of the system in the trap. This is how Bose-Einstein condensation occurs in their external potential. What will be different? For example, for parabolic trap, this power will be different. As a problem which I suggest to do, you can take a book of Bose-Einstein condensation, about Bose-Einstein condensation. There is a nice book of Pethick, I can give you a reference, which discuss in very simple way in any details what happens in a trap. You can do this calculation yourself, and for example, for three-dimensional trap, it will be T over T naught to the power 3. So the power law will change. But the spirit of what I was telling you, namely that there is a macroscopic number of particles occupying the lowest possible energy state, remains true. For the box, the lowest possible energy state corresponds to energy equal to 0. For the potential, the lowest possible energy state corresponds to the ground state of the system. The first level which you get in your external potential. Okay? Good. So, energy. Can you hear me well? I mean, I usually speak louder. Usually people complain that I speak too loud But I think for those who sit in front of computer, you can take your speakers a bit down and it solves the problem. In a room, it's more difficult. But if you have a problem to listen to me, please tell me I'm using your microphone because I cannot read the chat. Okay, energy, thermodynamics of BC. So, the same way energy is equal to sum over P, epsilon P times N P bar. And you remember that epsilon P is equal to P squared over 2N. Now, I will do the same. I will replace my summation of a quantum state by integration. However, in contrast to my calculation for the density of the particles, where I need to separately take the term with momentum equal to 0, I see that the term which energy equal to 0 is multiplied by 0 energy. So it doesn't contribute to the sum. Therefore, I don't need to do the same. Namely, I can directly replace my summation by integration because there is no macroscopic number contributing to the energy. This macroscopic number is multiplied by 0 and therefore is equal to 0. So this is the volume integral dp over 2 pi h bar cube. Here we have a p squared over 2m divided by e to the power epsilon p minus mu plus modulus mu divided by temperature minus 1. This is the equation which defines energy. Let me look at this energy at temperatures equal or below to T naught. So now I will consider this general expression for temperature smaller than T naught. What is the simplification? Below T naught, the chemical potential is equal to 0. So therefore, I write again the energy is p squared over 2m. Therefore, the system is isotropic. I can integrate over angles. So I have a volume. I have a 4 pi m square root over 2m divided by 8 pi cube h bar cube times integral energy, which stands here, times square root of energy, which gives me energy to the power 3/2 d energy divided by e to the power energy over temperature minus 1. Again, I do the same trick. I make integral dimensionless. Therefore, I divide it by temperature to the power 5/2 and multiply it by temperature to the power 5/2. So I have another integral similar to this. So instead of square root of z, I will have z square root of z. So this is yet another number. And I don't need to take care about this number. I know that this is number and that's it. So I can write down, therefore, that energy for temperature smaller than T naught is just equal to some number. I call it gamma, volume, temperature to the power 5/2. Okay? For the purposes of my calculations, it's enough. It's just culture of doing calculations that whenever you start with the integral which has a dimension, you can transfer it to the integral which refers to integration of a dimensionless variable of some dimensionless function. So, good. Now I will massage this integral and draw some conclusion about equation of state based on the analysis of this integral. So if you remember for the thermic gas, I computed thermodynamic potential omega. and since omega is equal to minus pressure times volume, it gives me equation of state. For the purpose of education, I will treat the situation for the Bose gas in a bit different way. I already computed energy. By the way, for the ground state energy, we immediately get, if temperature equal to 0, the energy is equal to 0. In the box, all particles are sitting on the level characterized by 0 energy. However, in order to show you how to compute in a different way, I will compute now specific heat. From specific heat, I compute entropy, and knowing energy and entropy, I will compute the free energy. And from free energy, I get equation of state. Okay, so specific heat, CV. This is D energy over D temperature at fixed volume by the definition. Energy, chemical potential, and specific heat are thermodynamic potentials or derivative of thermodynamic potential. They are extensive. They are all proportional to the volume. Therefore, for the specific heat or entropy, it's usable to define the specific heat per unit volume. So this is why I will use small c for the quantities per unit volume and capital C for the extensive variables proportional to the volume. So far, I'm dealing with extensive variable. I take this expression, I'm interested in the specific heat, energy, and equation of state below T node. Therefore, by differentiating this expression over temperature, I have a 5½ gamma volume temperature to the power 3½. Whatever gamma it is, I'm not specifying what this number gamma is. Okay, therefore, specific heat CV small, which is CV divided by volume. This is gamma temperature to the power 3½ and multiplied by 5½. Okay, then we know that CV, on the other hand, now let me refer to small c, is T ds over dt, where S is the entropy of the system. So in order to obtain the entropy, which is also extensive quantity proportional to the volume, we can solve this differential equation very easy. If we have a CV dependence on T, we can write down that this is the integral over CV as a function over T prime divided by T prime d T prime. And the integral is taken from 0 to T. This is how entropy depends on the temperature. And we also use that at 0 temperature, the entropy is equal to 0. We have non-degenerate situation. There is the ground state is not degenerate. Okay? There is no residual entropy. Yeah.
Which CV is that? Is that CV the extensive or the other one?
No. For the moment, extensive. I use capitals for everything. But it doesn't matter. You see that the equation means if I divide by the volume left-hand side and right-hand side, I will replace capital letters by small letters. So far, I'm doing extensive. Okay, if I plug in CD from here, what I get is integral from 0 to temperature. Here, I have 5½ volume times T prime to the power 3½ divided by T prime d T prime. So T prime this 3½ 1/2. Integral square root of x dx gives me 2/3 x to the power 3½. Therefore, S as a function of temperature is equal to 5½ divided by 2/3 multiplied by 2/3 multiplied by volume multiplied by gamma multiplied by temperature to the power 3. Okay, so the entropy is 5-fold. What is this chart? Entropy is equal to 5-fold gamma times volume times temperature to the power 3/2. Okay? Very simple.
Professor.
Yeah.
Just now you mentioned about non-degenerate situation. Can you explain more about it?
It's quite complicated. When you have a non-degenerate situation, there is residual entropy which corresponds to degeneracy of your ground state. Suppose you have a Bose-Einstein gas with a spin equal to 1. We are considering spin equal to 0. Singlet situation, it's non-degenerate. For spin 1, for example, you will have a 3-fold degeneracy of the ground state, because the degeneracy of state S of each atom is 2s plus 1. If 2s plus 1 for spin 1 is equal to 3. For spin equal to 0, 2s plus 1 is equal to 1, right? The entropy of the ground state, residual entropy, is proportional to log of the degeneracy factor. For spin equal to 0, 2s plus 1 is equal to 1, log 1 is equal to 0. For spin equal to 1, log 2s plus 1 is equal to log 3. This is the residual entropy of the ground state. Therefore, when you integrate from 0 to temperature, you also need to add a constant, which is entropy of the state, and this is the only difference. So for simplicity, I assume that the ground state is non-degenerate, therefore there is no residual entropy. If ground state is degenerate, you need to write the residual entropy, which is the entropy at temperature equal to 0, which corresponds to logarithm of the degeneracy factor. Okay?
Okay.
Yeah, Professor, just a silly query.
Sorry?
I mean, for the sake of thermodynamics, if we use gamma with CV, one will begin to think about the CV, the gamma that relates CV and CP.
Well, CV and CP corresponds to different specific heats defined at a constant volume or constant pressure. In the next minute, I will write you Gibbs free energy. And Gibbs free energy allows you to define CP as well for ideal Boltzmann gas. You need to define difference between CP and CV. I leave this to you as exercise. What I need is to write free energy, Gibbs free energy, which is F. This is what I'm writing now. And of course, at the end of my calculations, I will just exclude gamma. This is why I did not specify what gamma is. My final result will not contain gamma. So Gibbs free energy, F, is equal to E minus T times S.
Sorry, Professor. I still didn't get the I mean the case when you talk about the degeneracy, because I see in the calculation there's no involvement of the spin here. So why there's a difference between non-degeneracy?
As I said, if I have a finite spin, I need to take into account that in the absence of magnetic field, each atom for spin 1 is 3-fold degenerate, because spin 1 is a triplet. It contains 3 components,
Yes.
+1, 0, and -1. So magnetic field lifts out this degeneracy, but without it, each state is 3-fold degenerate. That even at temperature equal to 0, you will get the logarithm of your statistical weight will give you logarithm of 3 times number of particles. So at the end of the day, you will get that the entropy of the ground state of degenerate system of spins is proportional to logarithm of 3, because for spin 1, it will be logarithm of 5 for spin 2, logarithm of 7 for spin 3, and so on and so forth. But for spin 0, this logarithm of 1 is equal to 0, which tells us that the singlet state, each atom is a singlet state, is non-degenerate, and therefore you have Nernst theorem, which tells you that the entropy at temperature equal to 0 is equal to 0. That's it. And this is what I used here. I used that at 0 temperature. Otherwise, I need to write minus S T equal to 0.
Okay, I see. I see.
That's it.
Yes, thank you.
For some problems, for example, if you have a Conda problem, in particular, well, I'm not going to details. For some quantum mechanical problems, the calculation of the degeneracy of many body state is very complicated problem. It's not that easy as I explained for spin 1, for example, of non-interacting particles. For some system, this residual entropy is very complicated object. This is the only thing which I would like to tell now. But for the purposes of illustration, I consider spin equal to 0 particles where the ground state is non-degenerate and the entropy of ground state is equal to 0.
Yes, I see. Thank you.
Okay, look, this is Gibbs free energy. I have all components for it. Energy is equal to gamma, volume, power, temperature to the power of 5 half, minus entropy is 5/3, volume, gamma, volume, temperature to the power of 3 half, times temperature. Therefore, F is equal to, this is temperature to the power of 5 half, and this is temperature to the power of 5 half, is equal to minus 2/3 gamma volume to the temperature to the power of 5 half. And you know, and we will have a tutorial about that to remind you that in thermodynamics, you need to write the thermodynamic potential, energy, Gibbs free energy, and Gold's free energy in the proper variables. For example, for energy, the proper variable, d energy, is P dV minus T ds. So for energy, the proper variables are volume and entropy. Therefore, I define the specific heat as d energy over d temperature at a constant volume. For other variables, it can be pressure, temperature. So you first of all need to express the thermodynamic potential in terms of its proper variables. And then you have so-called thermodynamic equalities, which can relate different derivatives of different potential. And this is indeed important. And in order to obtain CP, namely D corresponding energy with respect to temperature at constant pressure, you need to find this variable, for example, F, and proceed with the derivative. This is the way how to calculate CP. I'm discussing specific heat at the constant volume. And again, on a tutorial, we will refresh. This is what you need to learn. If I wake up you during the night and ask you what is this, you need to be able to give me an answer after the course of statistical mechanics. So it should be engraved in your mind forever. So, pressure is minus dF over dV at constant T and mu. So for example, dF you get as a PdV plus S dt. You will make Legendre transformation. And all these equalities can be written down in, say, 1/2 of the blackboard. I'm not going to do it now, because otherwise I will be just occupied with a simple thing which you're supposed to learn during your class of the lectures of statistical mechanics. So, finally, I take this derivative, I get gamma temperature to the power of 5/2 with a coefficient 2/3, and therefore I get P times V is equal to 2/3 gamma volume to the temperature to the power of 5/2. But this is the energy. So therefore, pressure times volume is equal to 2/3 energy. This is my equation of state. Okay? This is the same equation which I obtained for ideal non-interacting Fermi gas by computing thermodynamic potential omega, which is just equal to minus pressure times volume. Here, I obtained calculating meantime the specific heat and entropy. And indeed, as we know, if you take a classical limit where the energy is just 3/2 times kB times m times temperature, then we will get the Mendeleev-Clapeyron equation that pressure times volume is equal to m kBT, Mendeleev-Clapeyron equation. So this equation of state perfectly describes both quantum limit and classical limit. And last comment about thermodynamics, we see from here that pressure goes to 0 if temperature goes to 0. In contrast to Fermi gas, where pressure doesn't go to 0. You can't go back to the calculation of Fermi gas. So why it is so? For temperature equal to 0, all particles occupy the state with 0 energy. The energy is equal to 0. Since energy is equal to 0, the particles occupying boson-Einstein condensed state do not contribute to pressure. They characterized by 0 momentum. They don't create any force. So this is the reason. So at 0 temperature, one has 0 pressure just because all particles are sitting in the ground state corresponding to the 0 energy. And this is one of the most important conclusions from the boson-Einstein condensation. Okay, so now I have half an hour and I would like to do some calculation. Some of the calculation I will sketch because I spent first 10 minutes for discussion of questions with you, but nevertheless, I will complete everything and we will get to the final answer. So I finished with the ideal non-interacting Bose gas. Now I'm going to consider Bose gas with weak interaction. I will quantify what weak is in a minute and we proceed with a simple calculation. Okay, I will call it weakly interacting Bose gas. So, in order to consider this Bose gas, I will start with the Hamiltonian, which describes me particles in the presence of interaction. So this many-body Hamiltonian, written in the second quantized language, is equal to, first of all, I have a kinetic energy, integral over dr prime. For the purpose of this part, I use h bar equal to 1. I have a psi dagger r prime minus nabla over 2m psi r prime. In principle, I can consider evolution of states. Therefore, these operators will depend on r prime and time. So this is kinetic energy. energy associated with the fact that my particles, for example, are in the external potential. Psi r prime t, dagger v r prime, psi r prime t. Okay? Psi are the secondly quantized operator as a function of coordinate and time. Then I have many-body interaction, and I will write it in the form constant g over 2 psi dagger r prime t psi dagger r prime t psi r prime psi r prime. So this is interaction. So usually we write this interacting term as a psi r psi x psi dagger y v x minus y psi y psi x. This is a standard way to write interacting term in the quantum mechanics. But if I use potential, this is my interacting potential, as a g times delta function x minus y, and this is so-called contact interaction, I will consider my particles point-like. Then, if it is delta function, I will come to this form. So it means that I assume that my particles are interacting only when they, in a semi-classical limit, assuming that I have a particles, not waves, and these particles like a billiard balls of a radius d, I assume that these neutron particles interact only when they collide. I can do more sophisticated definition using quantum mechanics, using the shape of probability density of your wave function. It will be pretty the same. The condition that my gas is weakly interacting means that d, the area of interaction, is much smaller than the mean distance between particles. The mean distance between particles is of the order of density to the power 1/3, inverse density to the power 1/3. Therefore, I have n d cubed is much smaller than 1. So density times effective size of interaction for quantum mechanical purposes, it is related to so-called scattering length. So the proper way to proceed from the semi-classical definition to purely quantum mechanical to define a scattering length. This is what we are going to do on Wednesday. So the density times proper scale, which is size in quote-unquote, or scattering length to the power d, should be much smaller than 1. This is a gas parameter. Since my particles are neutral, contrast to Coulomb gas, which we considered last week, we assume that weak interaction corresponds to low density limit. There is no long range interaction. Okay? Is it clear why the Hamiltonian is like that? And what is inside the Hamiltonian? Because if you digest the Hamiltonian, I would like to make 2 more steps. The step number 1, from canonical ensemble, I'm coming to the Gran canonical ensemble. I define purely H as H minus mu n.
Sorry, Professor. Can you explain what is secondly quantized operator? I know it's related to second quantization, but
Sorry, you had advanced quantum mechanics.
yeah.
I'm very sorry. I cannot stop now and start to tell you about second quantization and first quantization. It will take me full lecture. I'm very sorry if you didn't get it in advanced quantum mechanics course, and today I sign your certificate for the first term, and I see that you all get very nice grades in advanced quantum mechanics. You just need to go to textbook and refresh it. the second quantized language and equation of motion is the core of my calculations. But I cannot go from first quantization to second quantization. No way. I simply don't have time for that. You know that there is a Schrödinger picture when you define a wave function and you have a Schrödinger equation. And you have a Heisenberg, or so-called matrix quantum mechanics, when you define operator and you define equation of motion for the operator. Since psi, a secondly quantized operator, the Heisenberg equation of motion for the operator is minus I d psi operator over d t is equal to commutator over h and psi. Okay? So this is Heisenberg equation of motion. So instead of working with the wave function, you work with operator. And as I said, instead of working with a fixed number of particles, which is canonical ensemble, I'm working with a fixed chemical potential. This is a Gran canonical ensemble. Therefore, I proceed with a curly H, which then needs to add term minus mu times psi operator r prime t dagger psi operator r prime t. So this is what I add to my Hamiltonian H in order to transfer from H normal to H curly. And the rest 10 minutes, I will show you how to compute this commutator and how to get equation of motion for the psi operator. And this equation of motion is the Gross-Pitayevsky equation, which I'm going to treat and find spectrum of weakly interacting Bose gas. Okay? Are you still with me? Is it only Macha has a problem with second quantization, or everybody has a problem with second quantization?
Yes, but I think maybe we can study it ourselves and then ask you if we have problems.
Yeah. We've come to this point because on Wednesday I'm going to start with the same Hamiltonian or even more general Hamiltonian written in the second quantized operator, not in a coordinate time representation, but in the momentum representation. I will not use equation of motion. I will use another, everything will be time independent. I will use another tools in order to diagonalize my Hamiltonian. Today I will be also diagonalizing Hamiltonian at the end of the day, but first I need to write equation of motion for the psi operator. Please go to the textbook if you still have a problem. We will come back to it. So I will need to delegate one tutorial or one lecture just to repeat with you second quantization for bosons and fermions. In many body physics, it's the core of everything. Any Hamiltonian which I'm going to write down will be written down in terms of secondly quantized creation and annihilation operator with a certain commutational relations. For example, here we have a Heisenberg picture, contrast to Schrödinger picture, and commutation relator for the Heisenberg operator, which depends on coordinate and time, are only defined in equal time moment. In particular, I'm saying that the operator psi and psi dagger, so r t, r prime t, minus psi dagger, these are operators. I can have everywhere r prime t, psi r t. These are Bose condensation related, delta function r minus r prime. But this operator must be taken in equal moment of time. Only then you can define the commutation relator in the Heisenberg picture. And I'm relying on the Bose statistics. These are bosons. For fermions, we have sign plus. Okay? So what remains is to take the Hamiltonian. In the left-hand side, we have a time derivative of the operator. In the right-hand side, we have a commutator. So let me show you with one term how to proceed with this commutator. You will do the same for remaining terms. I plan to do it on the blackboard, but I don't have time for that. So I show you with 1 or 2 terms how to do it, and you will proceed with the same. So I have 1, 2, 3, 4 terms. So I need to compute 4 commutators, and let me start with the first. I'm computing right-hand side. First of all, there is an integral over dr prime.
Sorry, Professor. Sorry. What's that last term?
Sorry?
Oh, I mean the Hamiltonian has 4 terms.
Minus mu n. So this is connection because I want to work with the Gran canonical ensemble. As I said, I want to work with a situation when the chemical potential is fixed, not number of particles. Do you know the difference between canonical and Gran canonical ensemble?
Yes.
In one case, we work with a fixed number of particles. In the other case, we work with a fixed chemical potential. And since we are going to work with a situation, you see, we have a condensate. So it's all the time exchange. Some particles go inside condensate, some particles go outside of the condensate. So neither number of condensate particles nor number of out of condensate particles is conserved. They're interchange. I mean, particles are going in and out. The total number of particles is conserved. But for the purpose of what I'm doing, it's more convenient to work with the Gran canonical ensemble. The chemical potential is conserved because system is in the situation of mechanical equilibrium. So, okay, commutator. I need to commute this term with the psi operator as RT. Let me write explicitly. So I have a psi dagger R prime T minus nabla over 2m psi R T R prime T psi R T. So this is the first part minus psi R T psi dagger R prime T minus nabla over 2m psi R prime T. So this is a commutator of the first term of the Hamiltonian, namely kinetic energy. This is a Hamiltonian psi minus psi Hamiltonian. So what I need to do is now to commute twice and cancel out certain terms. So first of all, let's look at this combination. You see, this is R prime R. Since the commutation relation is a psi minus psi without dagger is 0. So this is R prime, R, T. Two creation or two annihilation operators just commute. Creation and annihilation operator commutator is equal to delta function. So therefore, I can interchange these operators. This is psi R, psi I prime, T. Now, since my differential operator nabla acts on a coordinate R prime, I can get it through. I'm still massaging the first term. So what I get after permutation of this operator and applying operator nabla is psi dagger R prime T, psi R T, nabla minus nabla over 2m psi R prime T. I commute and I act nabla. So now I need to permute these two. Psi I prime T psi R is equal to this term minus delta function. So this is then for the first term. It's equal to psi R T psi dagger R prime T minus nabla over 2m psi R T operator minus delta function minus the delta function will remove me the integral. Okay? This term, I'm dealing with this term. This term cancels out this one because it has perfectly the same structure with a sign plus. Therefore, I continue for the integral. It's integral over dr prime. I have a delta function r minus r prime with a sign minus, and minus delta over 2m psi r prime t. Okay? So the first commutator, first one, gives me plus nabla over 2m, nabla over 2m psi r t. Okay? Then, with this term and with the term with the mu, you proceed with the very same way. And you get pretty the same result. So after permuting operators, you have a term with a delta function, and you have a term which cancels out the second term of the commutator. With this term, where you have a for creation and annihilation operator, you need to compute several times. Some commutators, for example, with this and this operator, will be simple because they simply compute permutation, and some of the operator, when you commute, will give you delta function and something which cancels out. Twice delta function, you have 1/2 multiply 2, you will get g times half. So what I suggest that using this procedure, you compute term by term. This one I did for you. With this mu and this, you repeat this calculation themselves. In principle, my last year lectures contain these calculations in all details. Those who do not succeed in computing this yourself, look at videos of previous year YouTube. When I complete all calculations, what I will get? I will get the equation, which is I d psi over dt. So I multiply the right hand side and left hand side by the sign minus, is equal to minus nabla over 2m plus vr plus g psi target psi minus mu times psi. So this is equation of motion for the secondary quantized psi operator. So everywhere I have RT, I have RT. What do we see? We see that this equation of motion very similar to Schrödinger equation for the wave function, for time-dependent wave function. However, we have here operator, not wave function. But the difference between this equation and single particle equation is that this equation is non-linear. We know that the quantum mechanics is pretty linear science because we have a superposition principle. So there is no room for non-linearity. Here we have many body interaction between particles. Therefore, there is a term which is non-linear with respect to your creation and annihilation operator. Sometimes in the literature, this equation is called nonlinear Schrödinger equation because there are many different nonlinear Schrödinger equations which appear because of the interaction effect in many body quantum mechanics. This particular equation with this sort of nonlinearity is called Gross-Pitayevsky equation. So this is a Gross-Pitayevsky equation, which is the equation of motion for the quantum mechanical operator, Heisenberg equation of motion. Okay? I showed you how to derive this equation from the first principles using the Hamiltonian, which we had and defined in the blackboard. Is it clear?
Yes, so Professor, you're using the commutators to finally get to the final equation, right?
Yeah.
I
You see, you can check. there is a minus here, there is a plus here. When I multiply it by -1, this term I derived for you explicitly on the blackboard.
Okay. So I actually have a question about the nonlinear Schrödinger equation. So I read before in some literature that when the Schrödinger equation becomes nonlinear, it becomes no longer quantum. I mean, can you elaborate about this? Thank you.
It becomes what? It becomes
no longer quantum yet, but maybe.
Sorry, I didn't get the word. It becomes what?
So I read that if the Schrödinger equation becomes nonlinear, it becomes no longer quantum mechanical.
In some sense, true. The phenomena of Bose-Einstein condensation is related to condensation of some classical field. We will see. We will find a solution of the Schrödinger equation, and we will see that these are sound waves. I already commented on it, saying that the quantum mechanics as a single particle quantum mechanic is linear phenomenon because we have a superposition principle. So the equation H psi is equal to E psi assumes that the Hamiltonian itself doesn't depend on the wave function. But what you said is not completely true because we have interacting system. We are going beyond single particle quantum mechanics. This is particle-particle interaction in many body systems. So this is the still quantum mechanical equation. If you like, I have H bar here and H square bar there. So in a sense, it still remains quantum mechanical equation, although it contains nonlinearity just because of the effect of interaction in many body systems. But condensation will be shown is related to sort of classical phenomenon of classical field appearing in this quantum field theory. This is the way to formulate of quantum field theory, not quantum mechanics, for the Bose-Einstein condensation phenomenon. I can start with the action. You know how semi-classics is derived. You deal with the action, and your action has a unit of h bar. Therefore, you expand in 1 over h bar. And this is a way to get, by the way, some nonlinear equations for the semi-classics. For the exponent, it will be linear. For pre-exponents, it will be not linear, and so on and so forth. Here, I can construct the quantum field theory from very beginning, starting with action. But it will take longer. I rather prefer to deal with the Gran canonical ensemble and derive equation for the Heisenberg apparatus equation of motion. Okay? Now, I have 2-3 more minutes. Let me sketch the problem, since, again, I plan to do completely different derivation and devote whole lecture on Wednesday for the derivation of the spectrum. Let me sketch something and request you to do these calculations yourself. And on Wednesday, I will ask you if some of you succeed or not. Then I probably start doing this calculation on Wednesday and then continue with a different method. So, what we can do now with this equation? We can linearize this equation under certain conditions. So suppose we have condensation of our states, of our particles, which means that the macroscopic number of particles occupy state with an energy or momentum equal to 0. Therefore, I can look for solution psi RT. We have a macroscopic number as, first of all, square root of n, because psi target psi is related to n. I first would like to relate it to n node. So n node if psi is square root over n node, psi is also square root. I forget about n node plus 1 and n node. N node is macroscopic number 10 to the power 23. I don't discriminate between 10 to the power 23 plus 1 and 10 to the power 23. So if I plug in the square root of n node, I will get, first of all, with accuracy, up to 10 to the power 23 square root n node here. Because psi dagger will be the same square root of n node plus a, some coefficient a, times exponent I kr minus omega t plus b prime e to the power minus I kr minus omega t. So I look for solution of this nonlinear Schrödinger equation as a very large number, square root over 10 to the power 23, plus some oscillating solutions. I told you that there is a macroscopic number of particles sitting in the condensate, this is this, and there is some particles sitting out of the condensate. For ideal Bose gas, all particles are sitting in condensate at temperature equal to 0. For interacting system, interaction is sufficient to kick out particles of the condensate. So even for 0 temperature, there will be some particles sitting out of the condensate, and we approximate it by considering plane waves. So if you take this and that for the psi, you see that I replace the operator by a certain function, which is already approximation. If I plug it into the equation, I can use the fact that a node is very large number. I would even write a node capital in order to emphasize the large. This is the way I normalize my wave function. So it will be normalized by the total number of particles. So by using the fact that a node is a large number, I can plug it in here, take into account terms which will be proportional to the n node to the power 3/2 and n node, and disregard terms which will be proportional to the square root of a node and do not contain a node. As a result, you will get system of linear equation. This is a way to linearize your nonlinear Schrödinger equation. Since you have coefficients a and b, you will get two linear algebraic equations for coefficient a and b. By requesting these two linear equations have a solution, you have a determinant of your 2x2 system of linear equation, you will get connection between omega and k. And this connection actually solves the problem of the spectrum, namely what are the excitations in the weakly interacting Bose gas. In the non-interacting Bose gas, you have spectrum equal to p squared over n. The answer for interacting, so omega k, is equal to square root. Here you have g times n node, which will be density, times k squared over n plus k squared over 2n squared. This is the result which you get out of diagonalization. If majority of people have a different difficulty to get it, we will start Wednesday with solution of this equation, and then I show you completely different way to diagonalize Hamiltonian and to get the same spectrum. What we see for small k, for k goes to 0, this term is k squared, k to the 4, this is k squared, omega k is equal to ck, where it is first of all sound, like acoustic phonemes. Second, your sound velocity is proportional to both interaction and density of the condensate. So to say, in the system of weakly interacting Bose gas, you have sound waves or Goldstone modes. And these Goldstone modes are related to breaking down certain symmetry. You have yet another phase transition in this system. And as we will see in the lecture after the next, this sound wave directly related to very important property of the Bose gas called superfluidity. Existence of the sound wave excitations in a weakly interacting Bose gas related to the fact of superfluidity in this system. So this is very exciting property, and we are going to spend basically 2 or a little bit more than 2 lectures for discussing of that interesting and exciting phenomena, which is closely related to Bose-Einstein condensation. But I told you that Bose-Einstein condensation occurs even in non-interacting systems. So macroscopic number of particles occupy state with a 0 energy and 0 moment. But superfluidity is attributed to the effects of interaction because the sound velocity is proportional to square root of interaction. If you take out the interaction, then you will get that your spectrum is precisely P or K square, P square or K square over 2. So try to do these calculations yourself. I explained you how to do it. If you will not concede, we will do it together on Blackboard. Okay, I'm done for today. Questions?
Yeah, I have a question.
Mhm.
So you're expanding the psi, the wave function around the mean field, but I mean it would be like the mean field plus the like deltas in the direction.
Field, I'm expanding it around of a large classical solution. So when I replace the operator by so-called C number, it means that I'm considering classical phenomena. I'm relying upon the fact that n and a node are macroscopically large numbers. So this is, in a sense, classical limit.
What
I'm
I'm
expanding around this classical. So, in a sense, this is classical or condensation, and these are fluctuations around this classical solution. And for the fluctuations, I use the plane wave fluctuations because the effects of interactions are big. So I plug it in here. First of all, I will get a connection between chemical potential and G, which is another very important property, which is called Einstein-Condensed theorem. I will write it down here. So by linearizing this equation, we will also get very simple equation that G is equal to mu n. Although this equation looks very simple, is it not other way around? No, mu is equal to G times n, sorry. Sorry. Mu is equal to G times n. This is a chemical potential of interacting system. You should not confuse it with the chemical potential of non-interacting system, which is not positive, either negative or 0. For interacting system, you see that chemical potential is positive, but chemical potential is proportional to the interaction constant. Again, no contradiction. You take interaction constant equal to 0, you will get mu equal to 0 in both condensed states. No contradiction. However, in interacting system, chemical potential is not is positive. It's proportional to both interaction constant and density. This is called Einstein-Condensed theorem. And then you will get the spectrum which I drafted on the blackboard. You linearize your linear equation using very large parameter, which naturally appears in the equation.
Yeah, so because I'm trying to compare it with the mean field approach, and you generally like you have the Goldstone modes, but you also have the other modes that cause energy, right? And it is not clear to me why this expansion is it's related to the mean field expansion.
Yeah, I would not call it mean field. when we will do superconductivity, we will indeed define and do everything with the molecular field. Here, it's utilizing the fact that there is a macroscopic number of particles. We are not going to get a closed equation, for example, for some density or whatever. This is in the core of mean field equation. Mean field, if you assume something and get closed equation. Here, we assume that this is not macroscopically large, and then we expand, keeping in terms only highest power of this term, and kicking off, dropping off terms which are smaller compared to leading term which we take into account. This is a different spirit. Therefore, I'm against to call it mean field.
Okay.
Mean field, again, if you look, for example, this PEFIC book, which is nice, then in a trap, you can use sort of Thomas Fermi approximation. So then you connect the special distribution of density with some external parameter of your trap, frequency of the trap. This I would call mean field because you assume something about density profile. In the way you do it for Thomas Fermi, by the way, did you have a Thomas Fermi approximation in the advanced quantum mechanics course?
We had it in electron and phonons.
Okay, so you know how to deal with this Thomas Fermi. Yeah. What I'm going to do on Wednesday will, by the way, those who would like to leave lecture, please feel free. If you don't have a question, we continue discussion, but if you have something to do, please don't wait. You are not obliged to stay. We just continue discussion and that's it. If you have to do something more important, you are free to leave right now. What we are going to do on Wednesday, we will write down the same sort of Hamiltonian, but I'm not going to rely upon delta function interaction anymore. I will consider some two-particle interaction in arbitrary form. Moreover, what I will be saying on Wednesday is equally applicable to long-range interaction. And for example, if we have a system with Coulomb interaction, charged Bose-gas, we will obtain spectrum which will not be gapless anymore. We will see that for the case of long-range interaction, the condition for Goldstone theorem, which I'm going to formulate on Wednesday, is not fulfilled, and therefore the spectrum is not gapless anymore. But for those who would like to learn more, we have a system which preserves so-called U1 theory. U1 theory, U1 symmetry, is a symmetry in quantum mechanics which allows you to put additional gauge factor to your operator or wave function. Your quantum mechanics and quantum field theory is gauge invariant. And your equations of motions are preserved. By assuming that you have a condensate, you explicitly break down this continuous U1 symmetry. And as a result of breaking down continuous symmetry in macroscopic system characterized by short-range interaction, you will automatically get the gapless mode, which is a Goldstone mode. And this is the essence of the Goldstone theory. This is what we are going to demonstrate in a bit different way in writing down this Hamiltonian, separating term with a condensate, dropping off the term which doesn't contain a condensate. We will get some Hamiltonian, which is simpler than that, but it's still non-diagonal. And we will take some of rotation on a hyperboloid, which is called UV transformation, in order to diagonalize our quadratic form. This is what we are going to do on Wednesday, and as a result of a direct diagonalization of the Hamiltonian, we are not going to solve any equation of motion. We will get the same spectrum. But diagonalization means that we will express our Hamiltonian in terms of non-interacting oscillators. So we will get very simple Hamiltonian, but the dispersion of this very simple Hamiltonian will give us the connection between frequency and wave vector, which will again tell us that we will have sound waves, Goldstone modes in the system with a broken U1 symmetry. Yeah. Okay.
Professor, earlier you said the reference for today's lecture is from Petik.
There is a nice book, I think it's John Pethick. It's maybe I can give you a more precise. Maybe now.
Which chapter maybe?
Look, if you take book in the library, you will immediately find out. I will just a second. Maybe it's Smith basic. I will. Yeah, the book is called. So it's again Bose-Einstein condensation in dilute gases, and this is what we are doing. And the authors are. Let me write it down. So C, J, A, C, and H. Smith. It's called Bose-Einstein condensation in dilute gases. And it's Cambridge University Press, and the year is, first edition is 2001, second edition is 2008. So Cambridge. It's absolutely great book. For those who would like to learn, please, it's written in a very nice and simple language, contains a lot of physical discussion. So this is fine. Basic.
Also, which chapter you took this from, if I may?
So, the first chapter is introduction. I strongly recommend to read it. It tells about superfluid helium. I'm going to discuss superfluid helium in the when I discuss superfluidity. It's 15 pages. 17 pages is a chapter called non-interacting Bose gas. It discusses density of states, condensate fraction, condensate phase, and specific heat. Like 20 pages. And tracking chapter number 4, maybe chapter number, so interaction between atoms. Gross-Pitayevsky equation is chapter number 6. So, chapter number 6, and there you also have a Thomas Fermi approximation, variational calculations, heating of the wave function, and condensate with bipolar interactions. So the same, yeah, for Peluche, I also recommended that. I will write you concerning your question separately. So the book is not terribly big. It contains, nevertheless, more than 500 pages. So I will probably take my words back that this is not big. This is 564 pages. But chapter number 1, introduction, and chapter number 6 is probably what you suggested to read if you want to understand more. Some chapters number 5, for example, 4, are related to discussion of this Bose-Einstein condensation in traps and optical lattices. I will not have time to do it in details, but I show you some slides in the concluding lecture about Bose gas, and I show you how these tracks are made, what are the cooling methods to cool down, because we define, by the way, what is the temperature. When I'm saying cool down, one needs to define what is the temperature of the system. If I'm saying that the temperature is, say, nanokelvin or picokelvin, what is the meaning of this temperature and how people measure this temperature. But as I said, those who would like to learn more about Bose-Einstein condensation, Bose gases, superfluidity, to my taste, this is the best preference, but of course, there are many other brilliant books and lecture courses about Bose-Einstein condensation. This is a rapidly growing field, especially after discovery of Bose-Einstein condensation in ultra-cold gases of alkali metals. Yeah. If you have more questions about literature, I can provide you some other books, but this one would probably be sufficient for, say, initial acquaintance with this phenomenon in more detail that I'm able to give you on the lectures. Okay? More questions?
Professor,
Yep.
in the early lectures, you said there is a possibility for optional courses. I don't know if that is correct.
It's definitely correct, but I'm ready to any suggestions, but we should understand that if, say, two persons want additional courses, this is what I would really not be ready to dwell in. I would really like to see that there is some critical number, and for me, critical number will be, say, 5, 6 at least, those who want to have this course. I'm sorry, I personally would not be able to teach course for 1 or 2 persons. It's too much job. I don't know. My colleagues might have a different approach. And by the way, when you select a supervisor, we didn't discuss this issue before, but again, my colleagues have their own approaches. I can tell you that during 15 years, 14, well, this is my 15th year being at ICTP,